Okay, so our last speaker today is Paweł Nurowski, who will continue with his mini course on simple non-holonomic systems on the plane. So Paweł, the floor is yours.
Thank you. So I will continue this what I started yesterday, and this part, at least, yeah, this part of this lecture is based on a paper with Andrei Agraciov, and then I will comment about this later at the end. Okay, so let me start at this moment that I was last time. So I'm considering a mechanical system of 3 ants on the floor, which move according to the 2 independent rules, and I will be considering these 2 cases separately. First, the rule A is such that it forces the velocity of any given ant to always point at a neighboring ant, as on the left picture. And rule B forces the velocity of every ant to be parallel to the line defined by the 2 other ants. So let's start with rule A, analysis of rule A. So what this rule says, it says that the velocity, so if I just consider position of free ants on the plane, and I will enumerate them by vector on the plane Ri, where I goes from 1 to 3, then I wanted the velocity of its ant is parallel to the line defined by the next ant and the actual present one ant. And here this ij goes from 1 to 3, and I will be counting I plus j modulo 3. Okay, so we can parameterize this configuration space by some Cartesian coordinates related to Cartesian coordinates on the plane. And in this parameterization, the movement of the system is given as a curve in this R6, and its velocity is like that. And now you essentially have 3. So each of these conditions for each ant is just a scalar condition. So we have 3 scalar conditions on the movement. So this, which is here, is translated into 3 conditions on these coordinates x, y of 3 ants and their velocity. So that's the linear constraint. So for each I being 1 to 3, we have one equation which is indeed linear in the velocity. Okay, so equivalently, we can say that the curves drawn in the configuration space by the ants obeying rule A must be horizontal with respect to the velocity distribution D, which annihilates the following free one forms. So this is essentially the same formula that was on the previous slide. And saying it differently, the velocities must be tangent to 3 vector fields which are given here. So the velocity distribution, so my configuration space now is R6 with velocity distribution spanned by these 3 vector fields on R3, and ants should move in such a way that they are always horizontal with respect to this distribution. So now we can take commutators to just calculate what is the next what is the derived flag of this thing, and one can calculate it very easily. And after this, one observes that the 6 vectors that I produce in this way, vector fields that I produce in this way on R6 are linearly independent, except on some locus which makes 0 of this thing here. So it follows that 6 vector fields are linearly independent at each point of configuration space, everywhere except the points on the singular locus where coordinates satisfy this. And now you can think what this thing is. You see there is some quadratic thing, so it is easy to guess that it is just the area of the triangle defined by these 3 ants at every moment. So in other words, this distribution is 3, 6 everywhere except the configurations that the ants are on a line, right? So somehow in this R6, there are all possible configurations. When they are on the line, this distribution stops to be free six, right? So now let me recall a few things about distributions. Again, I said it yesterday, but I repeat in this particular situation. These free distributions have differential invariance. So we know what does it mean that two distributions are locally equivalent. So in particular, the statement about rank-free distributions having invariance means that there are locally non-equivalent rank-free distributions on six manifolds. Among them, the free six distributions are generic. So if you randomly choose a free six distribution, it will be randomly choose a free distribution on six manifold. It will be this free six one. And this growth vector distinguishes them locally from, for example, distributions with growth vector free five. So this free five distributions in dimension six are rank-free distributions in dimension six, such that in this sequence, this d-2 is integrable and has rank 5. But anyhow, I repeat, there are locally non-equivalent free six distributions. And one way of characterizing distribution is to calculate the algebra of symmetries. I recall what it was. These are such vector fields on the configuration space that commutators of these vector fields with all the vector fields from the distribution sit in the distribution. And it is known that for the rank free distributions with the growth vector free six, the maximal algebra of symmetries is attained for the distribution locally given in Cartesian coordinates in R6. Q goes from 1 to 3 and P goes from 1 to 3. And this can be defined as annihilator of this form in R3. And such distribution, so it is a free six distribution with maximal symmetry, and this maximal symmetry Lie algebra is isomorphic to Lie algebra spin 3-4 or spin 4-3. Okay, so that's what much we know about free six distribution. So the first question immediately to be asked: what is this how to characterize this free six distribution of ANS among how this relates to the most symmetric distribution, at least locally. So by the physical setting, since we only use the notions of points and lines on the plane and tangent, so that's this distribution definitely is symmetric with the symmetry group, projective three-dimensional group PGL3, right? So the group of symmetry must be at least 8-dimensional, but 8 to 21 is still a lot, right? So
yes, it is homogeneous.
yes, it is clear that it's homogeneous. Yes, it is. Because this, it is how I define them. I define them. These are just points and lines on the plane. So this configuration is definitely PGL3 symmetric, right? So I didn't put any ingredient but points, lines on the plane. This must be symmetric, and you can calculate it actually. So actually, you can calculate the symmetries explicitly. You can solve the symmetry equations. That's the simplest way of doing it. That's the simplest way for me. But the simplest way for people who are like Andrei Agrachev, for him, or Gilbert, they would immediately say that everything here is PGL3 symmetric. It might be higher, but that's what I was hoping, but it is not. So if you just solve the symmetry equations, and it is very easy in these Cartesian coordinates that I gave, I can solve them, but Maple solved it in a fraction of seconds. He finds all symmetries. So there are only 8 symmetries. So it is really the maximal algebra of this thing. Okay. So as you see, it is very far away from 21. But it's homogeneous, and actually, you can see that it is homogeneous space of PGL3 divided by the maximal torus there. So it is a 6-manifold. So you can think about these ants moving on this homogeneous space. So that's the global picture of this what I have here. Perhaps I should also mention that if you just look at this vector field, so these are vector fields on R6. but they come out from the vector fields in R2, so from the symmetry of R2, right? So if you just think about them, you recognize that the first two, x1 and x2, these are just translations they correspond to the translations in the plane. The x3, x4, and I think x5 minus x6, they form a area-preserving affine transformations on R2. So this is good to remember that among these vector fields on this R6, there are these 5 that corresponds to transformations that are area-preserving in R6. Okay.
So is it true that trajectory of one of the undefined cells, trajectory of the other, you know, trajectory of one of the
Good question. I don't think so. If one moves, I don't know. But anyhow, you should remember, because people are thinking that I want that. Remember that in my story, I admit these broken trajectories, so they can move. I don't need that these curves are just like smooth, because people were saying that they will be just going if they were on the square, they will be going on a spiral. Okay, they will be going on a spiral but they can go both directions always, right? As you remember in my picture here. Sorry, I drew explicitly what I mean. I mean that he can go this direction or this direction or this direction, and at any moment he can change the thing. If one changes, the other changes, right? So I admit these broken curves, and actually that's the point here. Okay, so that's much about this rule A. And I want to pass to the next one, which I was believing that is the same, but it's not. It's actually not. So we still are, our configuration space is essentially the same. We are in R6 with this, but now the rule has changed. I don't know if you remember what I had before. I had here I plus 1 minus I, and now it's I plus 1, I plus 2. Not very much difference, right? And then if you do the same, then these 3 equations that define the non-holonomic constraint. And these are the forms, these are the vector fields, and now you start doing their commutators, right? And here the story is very different, because if you just calculate what they do, these 6 vector fields are linearly dependent at every point. They're linearly dependent at every point. So the rank of the derived distribution is smaller than 6, and the velocity distribution for the rule B is not bracket generating. Actually, it's very easy to find relation. There is precisely one relation between these vector fields that makes them 0, and that's the relation. So I repeat, this shows that the velocity distribution for the ants moving under rule B has the gross vector 3, 5. Remember that there is this possibility, 3, 5. The first derived distribution has rank 5 and is integrable. The 6-dimensional configuration space M of ants being in a motion obeying rule B is foliated by 5-dimensional leaves. And once ants are in the configuration belonging to a given 5-dimensional leaf in M, they cannot leave this leaf by moving according to rule B. So they are confined to these leaves, right? So immediate question is, what is the physical quantity that defines a leaf, right? What is the invariant here that invites the leaves? There is a quick algebraic answer to this. One can very quickly see that the differential of these 3 one-forms that annihilate the distribution is 0, meaning that we have this, and this F turns out to be area. Okay, so if you just think about what does it mean, it means that the these integral manifolds are manifolds of a given area of the triangle. So in other words, when these guys are moving on the plane, they are moving in such a way they do a lot of stuff, but actually once they are in a triangle of a given area, they will be still in the triangle, but the area will be the same. So some kind of area preserving movement on the plane. So that's the proposition. The triangle with vertices formed by three ants moving according to rule B has in every moment of time the same area. So these, I told you algebraic proof, but if you think about it, just a second, you understand that it must be like this, right? Because every movement of them consists of three primitive moves. So think about this. You can just, if two of the ants don't move and one moves, it's still according to the rule. But if the one moves, it can only move parallel to the base of the triangle. So when the one ant is moving, the triangle is changing, but the area of the triangle is the same because the height of the triangle is the same, right? And if the other moves and they stay, that's the same. And actually the general movement is superposition, linear superposition of these three movements. So they must preserve the area, right? Okay, so that's what it is. So we see that the movement of the ants according to rule B stratifies the configuration space. Once in an initial position, the ants defined a triangle delta of area A. They move on a 5-dimensional submanifold MA of M, whose configuration points correspond to triangle delta prime having the same area. For each fixed A, for the three vectors are tangent to the 5-manifold MA. So this Z1, Z2, Z3, this distribution is always tangent to a submanifold of corresponding to some area of the triangle. So what we have now, if we forget about other leaves, we reduce to 5 dimensions, and now we have 3-5 distribution. So they define a 3-5 distribution, these ants, and we can just restrict to configuration space of ants confined to one of these leaves, right?
The equivalent
Yes, except of this horrible thing where area is equal 0, that's the same. Yes.
But it is clear.
Yeah, okay. First of all, for me, it is clear from the equations, because if you look at the equations, you see that this parameter makes no sense. If it is not relevant if only if it is non-zero, right? Okay, so there is this 3-5 thing, and it is known that 3-5 distributions define 2-3-5 distribution. So given 3-5 distribution, there should be a rank 2 distribution such that it's D minus 2 is D. So somehow it's an algebraic fact that you can, with 3-5 distribution, you can get 2-3-5 by taking sort of square of this 3 distribution. Okay, but in this case, definitely there is a 2-3-5 distribution. So it is easy to check that if I take Z1 minus Z2 and Z3 minus Z1, then there is a rank 2 distribution, which is actually 2-3-5, because one can calculate it simply. So you calculate commutator of this one with this one, you produce that one, which is the derived one. But remember that there was this dependence relation, so we can transform it to this one, and therefore you see that the commutator is like spanned now by Z1, Z2, Z3, and so the commutator, as I already said, is still tangent, but you can see that the commutator of Z1 minus Z2 and Z1 minus Z3, when wedged with Z minus 1, Z2, Z3 minus Z1, is Z3, Z1, Z2. So actually it produces the third vector of the distribution. So it's really, remember that recall that the free distribution was spanned by Z1, Z2, Z3. So using Z1 minus Z2 and Z1 minus Z3, taking the commutator, I produce the third one. So it is really, it's really square. This calligraphic D is really the square of the rank free distribution, right? So now this shows that for each A equal constant, the commutator is tangent still to the manifold, and then the first derived distribution of D is precisely the rank free distribution. Okay, so we have 2, 3, 5 distributions here. So so the 6-dimensional configuration space M of 3 ants moving on the plane according to rule B is foliated by 5-dimensional submanifolds MA consisting of configuration points defining triangles of equal area A on the plane. The ants obeying rule B must stay on a given leaf of the foliation during their motion, and their velocity distribution of rank 3 defines a rank 2 distribution, calligraphic D, which is the square of D. And the rank 2 distribution has gross vector 2, 3, 5 on each leaf of this foliation. So we created 2, 3, 5 distribution out of movement of these ants. And we recall that these 2, 3, 5 distributions have local invariance, and in particular, the most symmetric among them now has this G2 symmetry. So now the question is, so this happens for remember that I made this most symmetric 3-6 distribution as the model here, like you take R6 with coordinates pi qi, and then was this there was these 3-1 forms like this, and the annihilator was 3-6 distribution. But if you now restrict in this R6, you consider hyperbola like this one, then this thing restricts to a 2, 3, 5 distribution, and this 2, 3, 5 distribution has symmetry G2. So that's the model here. But I created some other 2, 3, 5 distribution, which was quite symmetric. So what this could be? How this relates to this one with the G2 symmetry. So it is a non-trivial task to guess the symmetries of D, because of this nonlinear relation that defines a leaf. Because if you, as I said before, for this 3-6 distribution of the ants, I took these vector fields and I solved this equation. The symmetry equations were very easy to solve. Here there is some nonlinearity appearing because of this nonlinear. So definitely in Cartesian coordinates, I cannot solve it and Maple cannot solve it. Actually, it's more important that Maple cannot solve these equations at all. It's just stuck 20 hours and they just forget about it. That's the point. If you just do it in Cartesian coordinates, you will not calculate this Cartan tensor. In Cartesian coordinates, no way. So you have to guess some symmetries. You have to guess some symmetries.
I can do it for you.
Go for it. You already told me that you can calculate symmetries of my snake, and you didn't. You didn't calculate the symmetries of my snake, and you also said that it's very easy to do it, and you didn't. And I tell you that if you just do it in Cartesian coordinates, or will be just trying inventing coordinates blindly, forget about it. No, it is actually, these snakes actually have bigger symmetry than this one, it turns out. But anyhow, so here you have to guess some symmetries and try to understand if you can extend them, right? So, so these symmetries, they should have something in common with symmetries of the plane. And the first thing that comes to your mind is just the area preserving affine transformations on the plane. So that's the first thing that you can check. And remember that when I was talking about this rule A, I had these 8 symmetries, and I told you that I had, so that was the same configuration space. And in this same configuration space, I had a representation in terms of vector fields of these area preserving transformations on the plane. There was the first two of these 8 symmetries there were translations, and the 4, 5, no, and 3, 4, and 5 minus 6 was the SL2 transformation. So I just take them and apply them to my distribution, and I just check that actually, if I just take the linear combination of them, I will see that first of all they are tangent to constant. All these symmetries are tangent to constant area because they are area preserving, right? So and moreover, they really the commutator of any guy from this symmetry with Z1 minus Z2 is in the distribution, and so definitely this five-dimensional symmetry algebra is a subalgebra of the algebras of symmetry. This five-dimensional algebra is written here, which is it is area preserving. So it is SL2R, it's semi-direct product of SL2R with R2. So it is SL2R acting in two-dimensional representation on R2. Right? That's this you can see immediately even in Cartesian coordinates. And now it is easy because now you know that at least you should be able to realize it on this because SL2R times R2 is five-dimensional algebra. So you definitely know that you can realize this movement on this group, right? Because this action is homogeneous on this, so somehow it is you can weave the group with these symmetries, and you can understand how the ants move on this group. So now it's easy, really.
So the total symmetry S will be SO3 plus SO3.
No, nothing is obvious here. until you calculate it. Okay, anyhow, the theorem which we proved with Andrei Agrachev is the following. The Lie algebra of all symmetries of this distribution is precisely this five-dimensional Lie algebra. So that's it. Nothing more. And
do you have another choice of Lie dimensional thing?
Say it again.
And you get naturally the three.
Yes, I think yes, it's unique. So these ants really define precisely this 2-3-5 distribution. Yes. It is unique. It is uniquely defined. Yes. There is no other. So you are asking me if there is other root of this no, there is not. That's precisely this one. Yes. Okay. So anyhow, that's what I'm say. So somehow this the distribution is one of the homogeneous models of 2-3-5 distributions. It can be locally realized on the 5 manifold being the group of area presenting affine transformations of the plane, and the Cartan quartic invariant of this D is of algebraic type D. So you can once you realize that it is just that the subalgebra of symmetries is this precisely this affine algebra, then that's what I was doing. I just adapted coordinates to this to the natural coordinates on this the group, affine group, and I reformulated all the statements about movement of the ants in these coordinates, and then you can represent these forms that define the distribution on this group. For the ants, you can reformulate them in terms of Maurer-Cartan form of this thing, and then do Cartan equivalence method for this thing, which is now very easy because everything is just expressed in terms of Maurer-Cartan forms on the group, and you can calculate everything. So that's how I was calculating the symmetry of this thing. I simply, anyhow. So it's so in our paper with Andrei, so we have proven that the symmetry algebra of ants under the rule B is precisely equal to the area preserving affine group affine as in theorem in two ways. Andrei have proven it by pure thought. He was not, once he understood that this is a subalgebra of symmetry, he understood everything. He was just saying, oh, this is like this like this, without any calculations. He knew, and he even guessed immediately what would be Cartan quartic, because he guessed that Cartan quartic could be either 0, which we would be very happy, or it must be type D. So it was from this pure thought of his, but then I didn't believe, I simply don't understand pure thought arguments. So I calculated everything in terms.
Semi-direct or direct product?
Say it again.
Semi-direct.
Semi-direct product. Semi-direct. Yes, this area preserve, I call it area preserving affine group. Okay, special, yeah, because it's SL2R semi-direct product is R2. Yes. What we did more in this paper, and I decided not to tell you about that. We have also calculated the abnormal extremals, which are these specially distinguished curves for D. It is why I really wanted Andrei, because I wanted to know what are these things. And they are quite interesting. They are quite interesting because eventually these curves, these abnormal curves, are governed by very interesting system of two ODs of Fuchsian type with 3 poles. And this is the final equation that you reduce the equation for these abnormal extremals, which is quite interesting. These are the generators of SL2R. It's quite interesting. So details of this thing is in the paper, and I can stop here. That's one possibility, which I would perhaps prefer it, and I hope that you also. But you can ask, what about G2? Can you realize G2 on the plane?
So as far as semi-direct product of SL2 and R2, as soon as you know that, and it is as soon as you know that, you know that it is not bigger, because SL2 semi-product with R2 does not is not a part of any bigger symmetry algebra.
That's what you know. That's what you know. You know all the subgroup. You know all the subgroups on G2. What do you mean?
What was the way again?
I just calculate Cartan quartic. I calculated Cartan quartic. And I calculated all the Cartan invariants of this distribution. That's what I did. My question, yes, that's it. I calculated all the symmetries then, because I use the Cartan equivalence method to just make this Cartan system for this distribution, and I reduce until I reduced back to SL2 in semi-direct product by times R2, and I know that it's just this model.
In SL2 times R2, you also have generating plane. It is generating plane, it's SL2, which corresponds to distribution. Right? You have SL2, semi-product with R2, and dog is generating 2 plane.
And so what?
Well, in these pairs, there are 2. With generating plane, 2 planes are over R 2 cases for SL2.
But this is one particular case, basta. It has symmetry precisely SL2R times semi-direct product result. What can I say more? If there are 2, this is one of these 2. They couldn't be 2, right?
It could change the sign from plus or minus this 2 when you change the area. The area has a sign, the area.
Area is positive as far as I remember.
It doesn't have sign.
Area is positive. I know this story. Okay, that's what I said, and I think that I will finish here, because the question is if I can have the in quotation mark realization of G2 group in terms of some non-holonomic objects defined on the plane. No, it's much longer. I will explain it next time. It depends what you mean. It is why I don't want to explain it, because it's just long story. I will write it up. Okay.
Thank you, Paweł. Any questions or further comments?
Maybe I can ask a small question.
We have a part of symmetries SL2 direct product with direct sum with R2.
You are asking me if I have such
Maybe,
mechanical
yeah.
system.
Yeah,
Example. No.
because if you have, it is impossible to have symmetry algebra. It will be automatically at least SL2 plus SL2. And for if you have a parameters, then you can expect that for distinguished value of parameter, it will be G2.
So this other one is this SO3 times SO3. So this rolling examples, so, right?
No, like a rolling example.
So rolling examples are this what you want to say,
no,
but I am quite surprised by this example of this thing, because I really was believing that these two rules correspond to the same movement. But
in these examples, you do not have parameters. Since your snakes, you have parameters, and you can hunt for interesting parameters. Here,
so what?
no, you cannot expect good hunting.
But I was not here. I was not hunting. I was doing 3-6 distribution, and somehow this 3-5 distribution popped up. I was not hunting for anything. I had a sleepless night, and I was just playing with these points on the plane.
Okay, more questions or comments?
Could I ask a question? Can you hear me okay?
Yes.
Great talk, Paweł. Really enjoyed it. Just a question about I guess your conformal structure. Have you looked at that for these ants?
Yes, I calculated everything. Yes.
I guess how many conformal symmetries does it have?
It has precisely the same amount of symmetry. So this metric.
So necessarily
is also symmetric with respect.
No almost
symmetric like this. Yes.
No almost Einstein scales there.
Yeah,
Then.
yes.
Okay. And what about for the in the 3-6 setting for rule A? Have you looked at
This I didn't study much, because I get fascinated by this. No, I didn't.
Yeah. No, but really interesting. Okay, thank you.
Okay, we still have some time for questions or comments. Okay, if there are no more questions or comments, let's thank Paweł again. And since this was the last talk of our workshop, I think this is the best time to thank organizers again. So Omid, Katja, Paweł, thank you.
Thank you, guys.
So maybe I should say something. I am very grateful for everybody who attended this conference, and I am really very grateful for people who came here to UAVA, because we tried to make a real conference like it was years ago. I think that we and we managed it, and all the participants that really came here to UAVA are my heroes, because it was not easy to come here, and we are really very grateful about that. The other thing I should say is that I didn't do anything with this conference. I was not preparing anything. This is really heroic job of Omid and of Katja. They were fighting with all possible obstacles that was preventing this conference of happening, and there were really, believe me, there were infinitely many obstacles. So I am really very grateful to Omid and Katja that they organized this conference. Thank you very much.